Right. Good afternoon, everyone. Thanks for attending one of the last sessions of SUSECon. So my name's Stephen Hardy. I'm one of the engineering directors in the Edge business unit at SUSE. And I'm going to talk to you today a little bit about what we're doing in the Edge BU around bare metal deployment and cluster management, specifically related to Edge use cases, but a lot of the tools and techniques I'm going to talk about are also applicable to enterprise environments as well. So we'll go over an overview of the Edge solution, a little bit of detail around the operating system that we're using, and I'll give you an overview of the deployment options we're supporting. I'll also then give a little bit more of a deep dive into the automation and management we're using for bare metal, and then we'll finish off with a demo. I'm not brave enough to do a live one, I'm afraid. It's going to be a recording. Yeah, that's going to give you an overview of the full process from end to end. And then hopefully we should have some time for questions at the end. So, quick overview of what we're doing in the Edge solution. So I guess to start off with, let's set the context. Edge is quite an overloaded term. It covers quite a large range of use cases, everything from near-edge data center deployments, which are essentially very similar to most enterprise data center environments, right the way through to tiny edge IoT kind of scenarios where you're looking at very, very small form factor and don't have very many options in terms of out-of-band management. And then the far edge kind of center category is a little bit of a grey area where in some cases you can do remote management of hosts and apply traditional techniques, and in other cases you have to rely on in-band management of the devices. So we'll touch on a few of these different scenarios, but mostly we're going to be focusing on the details around near edge and far edge where you can do out-of-band management, which is using techniques which you could potentially see in data center environments as well. So fundamentally, in the Edge group, we're focusing on very, very large-scale problems. You have customers who are dealing with global deployments in multiple regions, multiple data centers, and they've got potentially tens of thousands of Edge environments that they need to manage. And they want to be able to do coordinated rollouts of updates so that they can keep all of their systems up to date and also manage their workloads in a coordinated way as well. So the common theme is needing some kind of zero-touch management of the system. There's a few techniques and approaches to that, but today we're going to talk about using out-of-band server management using protocols such as Redfish, which is a common approach in many data centers as well as quite a few edge locations. So we're also going to talk a little bit about network constraints. Quite often in edge environments, you don't have direct access to the hosts. It's going to be routed via multiple networks. You typically don't have access to use L2 techniques like DHCP and PXE boot. And so that's another constraint. Often you would also in telco situations have requirements for advanced network techniques, having multiple NICs, multi-homing, bonds, VLANs, these kinds of things. And so you need a tool chain that is capable of accounting for those additional requirements. And then something which we've been talking about a lot this week is Kubernetes as providing a consistent API. And there are ways which you can manage your infrastructure in the same way as your workloads, use the same set of APIs, the same API surface, and not have to manage with multiple tools in your environments. So when you start looking at the potential solutions, it's a little bit overwhelming. Not everything on this diagram is necessarily supported as part of the Edge solution, but is to give you an overview of the number of options in the ecosystem. There's a large number of different choices you can make in terms of technology and integration, and what we're trying to do in the Edge solution is to provide a fully validated stack of multiple components that we ship and support and version together. And so the idea is that we build on the components which are available from other parts of SUSE and elsewhere in the ecosystem, and we build a fully validated stack that our Edge customers can consume. So we'll dive a bit deeper into some of these as we go through the deck. But this gives you a slightly more detailed picture. So the fundamental concept is you have a management cluster, a management stack, and here typically you would be dealing with GitOps style techniques so that you can manage very large scale environments in a repeatable way, grouping your downstream clusters and applying a common configuration and managing versioning in a scalable way. You could also, for proof of concept type of deployments, use the Rancher UI as well. That's a valuable additional option for when you're doing the first steps before you have full automation in your environments. So we're adding a few additional tools into the mix here. In addition to Rancher, we're also making use of the CNCF Cluster API project, which is an upstream project aiming to enable infrastructure management via Kubernetes. And we're also enabling a tool chain called Metal Cubed, which is, as I'll describe in a bit more detail, an infrastructure management plugin for Cluster API, which allows you to deploy bare metal via the Cluster API abstractions. And then on the other side of the slide, you've got the runtime stack. So, for telco customers, this is very much about enabling containerized network functions and virtualized network functions, which can be achieved via KubeVirt in the Edge stack. And then there is additional components which you can choose to integrate as well, such as NuVector for additional security functions and Longhorn for distributed storage. And then the core of it all is the SleeMicro OS, which I'll talk a bit more about in a couple of minutes, and also the Kubernetes distributions, where there's a choice between the lightweight K3s option or the RK2 option, which is the primary choice for our telco product, which is called Adaptive Telco Infrastructure Platform, or ATIP for short. So all of the components I'm describing here are also part of the ATIP offering. So this is giving you an overview of the end-to-end flow. So the fundamental approach is to enable GitOps via all of the APIs that you're driving here. So you're going to have some templates which are checked into a Git repo. You can have that versioned over time, and then have the management cluster consume those templates and manifests, and ultimately manage your estate of downstream cluster hosts. And so you can also use the same tools and techniques to deploy workloads on top. And there's several ways you can approach this. It's pretty flexible. You can layer your dependencies with different GitOps workflows using a tool called Fleet, which is provided via Rancher Prime. And so all of the choices we've made have been to enable this GitOps technique and to aim to make it a very scalable solution, which is easy to manage when you have a very large number of downstream clusters. So let's touch a little bit on the operating system. So obviously SUSE has been around for a very long time and has been shipping Linux for many years. We've made the choice to build our Edge solution using SleeMicro, which you heard about in the keynotes earlier today. This is a very natural fit, I think, for Edge use cases. It's optimized for a smaller footprint, which is helpful in Edge locations where often you will have, runtime resource constraints, also maybe thermal footprint constraints. You also probably trying to, in some perhaps retail settings, you might be trying to build things down to a certain price point. And obviously you also have a minimized attack surface because you're not running any components in the OS that you don't actually need. So it's a very natural fit for running Kubernetes on top, where you can run containers and also use it as a virtual machine runtime as well. And so there's several options for deploying SleeMicro, which we're supporting in the Edge solution. I'll touch on the different options, but then we'll deep dive into one of them. Another thing to maybe call out from an operational point of view is SleeMicro has an immutable file system. It actually uses BTRFS to enable that. It does a snapshot and allows you to do rollbacks to a point in time if you need to. And it has a tool called transactional updates, which basically makes that whole process a lot easier to manage. And that's something which we've been integrating into the workflows and tooling that we use in the Edge solution. Also, for some of our customers, real-time performance is important, particularly network functions for some of our telco partners. And so there's a real-time variant which uses the preempt RT kernel. And relatedly, there's also support for the various accelerated network drivers and DPDK, timing support, and other dependencies that you would need to set up a full telco stack, including RAN use cases. So we're looking to enable core network functions, but also RAN environments where you have potentially much stricter performance constraints. So we're getting into, you've got your operating system, you've decided which Kubernetes version you're going to use, now you need to deploy the stack. And we do have several options here, and it really depends on your existing environment and also the use case that you're solving for. So in the green box, there's image-based provisioning. So we've got a tool called Edge Image Builder. There was a nice talk about that earlier in the week, which you can go and look at the recording for. And this basically allows you to do a much easier generation of a customized SLE Micro base image, and it'll allow you to do full automation of your first boot configuration, including setting up Kubernetes, potentially even deploying your workload on top if you don't have another way to handle that. And then the next option in the orange box is phone home network provisioning. So this is the factory provision workflow, which uses a tool called Elemental. And this basically allows you to do a pre-image server, the factory provisioning workflow, boot it and have it phone home to the management cluster where you're running Rancher, and then do a late binding workflow such that you can then consume those discovered hosts into your downstream clusters. And then the directed network provisioning is the zero-touch flow that I was describing earlier on. So you have some known hardware in your edge locations. It's going to be in a rack with out-of-band management controllers, typically, iDRAC, ILO, Redfish, these kinds of interfaces which have become very common in recent years. And you can then drive the entire process from power on to provisioning without any user intervention at all. So we're going to deep dive into exactly how that process works. And so if you want to find out a little bit more about the other flows, Edge Image Builder is the first tool I mentioned. There was, as I mentioned, a nice session which you can go and look up when the recordings are published. If you want to find a bit more about the phone home network provisioning, you can look at Elemental, and I've also got some links to our product docs, which I'll show at the end. And so the directed network provisioning is using some tools called Cluster API and Metal Cubed. And that's going to be the focus where we'll deep dive a little bit more as we go through this talk. So we'll focus in now a little bit more on this end-to-end deployment and management flow using Cluster API. So just to kind of set the context, this is the flow that we're trying to achieve. So you have a rack of hardware, potentially many hundreds of nodes, or potentially even many thousands of nodes, depending on the environment. You're going to rack and stack the hardware, and then at that point you don't want to have any further interaction with it. You're going to be able to interact completely remotely. For example, you can ship a rack to an edge location or have a replacement node installed, and then every management operation can be performed remotely. And so the process would be you enroll those hosts into a management server, and then there's a process of inspection where basically we boot the host, and then we will look at the hardware on the host. And so you can do things such as subcategorize your host depending on whether it's got a certain type of NIC or if it's got a GPU or other characteristics. We also discover additional information such as LLDP data and the connected VLANs and other environmental data. So you would be able to do pre-validation before you actually do any deployment, and you have a higher degree of confidence at that point that everything's going to work as you would expect. The next stage after that is to actually create a downstream cluster using those hosts that you've enrolled. And again, this is a fully automated process where you would install the operating system, bootstrap the Kubernetes cluster, and then from that point you could also deploy your workload in an automated way as well. So all of these underlying components are pretty flexible. We make heavy use of Helm, as is the case in many other parts of the SUSE stack, and we're leveraging Rancher, which is also investing heavily in integration with Cluster API, and so this is very much a solution that is well aligned with what the other teams at SUSE are doing. So this is kind of a slightly more detailed view of what this actually looks like. So you've got a management cluster, which is running Rancher. You have Cluster API controllers on there, which we'll talk about in a little bit more detail in a moment. And then the tool which actually interacts with your hardware is called Metal Cubed. And this is the tool chain that can interact with the Baremetal management controllers, the Redfish, iDRAC, ILO interfaces, and it can drive the entire process. So we're actually making use of Redfish virtual media primarily, and this enables you to avoid any PXE boot L2 network dependencies. It attaches a disk image to the management controller. It boots the virtual media, virtual ISO image, and then from that point it's a fully automated flow. So that disk attachment and everything is all handled in an automated way. And as I mentioned, there's an agent image that then boots in the pre-provisioning phase. This is going to gather information about the hardware. It's going to perform disk cleaning, so you can make sure that there's nothing on any of the disks before you install the OS. And then ultimately, the primary function is to install the OS, so you can then bootstrap the environment. And so there's quite a bit of flexibility in this flow. You can provide additional first boot configuration. If you need to do special customizations to the OS, that's absolutely possible. But this is the overall flow that we're seeking to achieve. And then in most production environments, you're ultimately going to have a requirement for high availability. There's a few approaches to enable that, but one of the simplest is that you deploy 3 servers at the edge location and then have a load balancer in front of those 3 hosts. Typically, again, you're going to have requirements to minimize the amount of hardware at an edge site, so you probably don't want a hardware load balancer. It's more power, it's more expense, it's more cooling. So we use a tool called MetalLB, which allows us to run a software load balancer in place on those edge servers, so you don't need any additional equipment to achieve this. And so just to kind of focus on the community side of this a little bit more, we're heavily dependent on the Cluster API, which is an upstream CNCF project that's been around for quite some time now. I think in the industry it's been gaining really quite good traction over the last few years, and it's a really rich ecosystem of multiple providers for different platforms. It started really focused on enabling multiple cloud provider use cases. So you want to be able to deploy a cluster easily on any of the hyperscaler providers. But then over time that has then broadened into virtual machine platforms and ultimately also bare metal as we're describing today. So it allows you to have a declarative approach to managing your infrastructure, and it's completely pluggable. So basically you can use the same tools, techniques and APIs to manage any environment regardless of what the infrastructure backend actually is. And again, we've talked about GitOps earlier on. This whole approach is designed to be integrated into a GitOps workflow. You can make use of any GitOps tool, Fleet being one option which we provide, or you could use any other GitOps tooling in order to apply these changes, because it's just Kubernetes manifests. The other thing is, once you've done the initial deployment, the big problem for all of us is the day 2 management story. You need to roll out patch updates, you need to upgrade the OS, you need to roll out a new Kubernetes version quite frequently. And so Cluster API provides some quite nice functions there where it can do in-place rolling upgrades. There's also some good discussion in the community around making that whole upgrade experience more customizable, which is something we're following quite closely. So if you're interested in this topic and want to maybe dive a bit deeper, there was a nice talk yesterday around the Rancher Cluster API extension, which is called Rancher Turtles. This is actually not currently integrated into the Edge 3.0 release, but it's something which we're working on. But this gives you a nice integration between Rancher and Cluster API, and there's also a tech preview of a UI that allows you to access all these resources in a very interactive way. So if you're interested in that, you might want to catch up on that talk when the recordings are published. And so this gives you a kind of an overview of the components and how it all hangs together. Cluster API actually provides quite a few different plug points. You can have multiple different providers, including several add-ons. But I'm going to focus on the core pieces that are necessary to actually deploy a cluster in this session today. So you have a bootstrap provider and a control plane provider. The bootstrap provider basically allows you to provide the config to actually bootstrap a Kubernetes node. This is what provides the first boot configuration that bootstraps Kubernetes and ultimately starts RK2 and any other pieces that are needed. The control plane provider actually coordinates the cluster itself, and so this is the thing that would allow you to drive rolling upgrades and other operations that have to consider all of the machines that are part of the deployment. And then the infrastructure provider is the thing that actually boots the hosts. So it could go to AWS with the AWS provider and boot an EC2 instance. It could go to an on-premise VM solution and provide you with a VM. But in this case, it's actually interacting via MetalCubed with the physical hardware and booting real bare metal in the data center or edge location. And so MetalCubed is the key enabler for bare metal, as I mentioned in this case. This again is another upstream CNCF project that has been around for several years now, and it provides you that infrastructure provider for Cluster API. The key API to understand in all of that is the bare metal host. This is basically a representation of your inventory. So you rack a server and you create a bare metal host CR, and that describes the connection to the BMC and several other aspects that you can configure. For example, in addition to the host preparation I described earlier, it's possible to do automated BIOS configuration. Depending on the vendor, in some cases you can do automated RAID configuration as well. It will do cleaning disks, and again, that whole process is extremely pluggable. You can actually plug in custom operations as part of that host preparation phase. For example, if you needed to register with a local inventory service or something like that, that would be possible using these tools and techniques. And so you gather all of the data prior to deployment, and as I mentioned earlier on, you can absolutely use that for automation around validating the inventory. It could also be used for grouping. As I mentioned, you can look at the bare metal host resources and apply a label, and once you've labeled them with a certain label, they can be used for different groups or different clusters, depending on the characteristics of the hardware. And so all of this comes together to allow completely automated image-based provisioning and upgrades on your bare metal, which will scale potentially to many thousands of downstream clusters. So this is a bit of a busy diagram, but it's to give you an overview of the APIs involved. And so the cluster API provides quite a few abstractions, and I mentioned earlier on it's very, very pluggable. But the key concepts to understand here are the top-level cluster resource, and this basically gives you the global configuration for your overall cluster. So this is going to describe things like the endpoint that's going to be used to connect to the API, the subnet ranges for the various networks that the cluster is dependent on, and any cluster-wide configuration is just defined at that layer. And then beneath that, you have this concept of a machine. So a machine is basically a request for a Kubernetes node. And so in this case, you have a request for 3 machines. That creates 3 metal cube machines, which is the pluggable abstraction I was referring to. And that ultimately then consumes a bare metal host, which is used to actually boot up your hardware and allow it to join the cluster. So that's kind of an overview. You can spend quite a lot of time looking at the CAPI docs if you want to dive deeper into exactly how this all works. But the main point is that there's this, despite all the boxes on the diagram, it's a relatively simple model where you have cluster, machine, and then some providers. And it's all a very, very pluggable, very, very flexible system. And so you also have the control plane and bootstrap providers I mentioned earlier on. And so in this case, the control plane provider is the one that's going to go and request some machines. We're going to request 3 machines, which causes your servers to boot up and ultimately provision. And then the bootstrap data is provided by the bootstrap provider. And this is going to give us all of our first boot configuration, which again is passed to the OS and used to bootstrap the cluster. So we're now reaching the point where we can see all of this actually work in action. So this is, again, just to give you a quick overview of what we're going to show here. So we're going to show you the Kubernetes APIs that we're interacting with, although I won't go through every field. We'll just give you a quick overview of what that looks like. We'll show you the bare metal hosts and what it looks like to define your inventory on the Kubernetes management cluster. We're then going to deploy a 3-node HA downstream cluster, which has been configured to use MetalLB. And then we're going to prove that MetalLB is working by killing one of the nodes. And then we'll wait for it to recover, and then we'll trigger a rolling upgrade to consume the new Kubernetes version. So that should hopefully give you a flavor of the full end-to-end life cycle, including some of the data operations. Okay, so just to recap, we're going to have 3 RK2 control plane hosts. This is a compact cluster where we have control plane and compute hosts combined. We're going to use MetalCube from a Rancher management cluster, combined with Cluster API to deploy SLE Micro on those downstream clusters, and then we're going to use MetalLB on top to enable load balanced access. So the first step is we've got a pre-provisioned management cluster in this environment. I'm not going to show how to set that up today. We're going to enroll 3 bare metal machines from our lab, and once they're available for consumption by the downstream clusters, we're going to trigger the downstream cluster provisioning using Cluster API. Okay, so the first step is you've racked your 3 servers, or you've got 3 servers which you have access to. You need to define some custom resource definitions or consume the bare metal host CRD on the management cluster. It's a pretty simple API, really. In the bottom here, we're just going to show the current state so we can watch as we go through the process. As I mentioned, there's work ongoing to enable Rancher UI extensions to manage all of this, but as of this point in time, you have to drive it via the command line. So it's really just two resources that describe your hosts in your data center. You need to have a secret that has your credentials to access the BMC, so your Redfish credentials. You then have a cluster role, which, as I just mentioned, can be used for grouping. If you have hundreds of bare metal hosts, you may decide to group them in various ways. And then you have a BMC connection string, which ultimately is the endpoint that points to the Redfish ILO IDRAC management controller that allows you out-of-band management access on the downstream cluster. So we've applied those three manifests. We've got three bare metal host resources on the management cluster, and as I mentioned, it goes through this phase of inspection. So this is booting a discovery round disk, basically, which has some code in it derived from an upstream component called Ironic, which is actually part of the OpenStack ecosystem, which it runs behind the MetalCube abstractions. And this is going to do all of the inspection of the hardware. It's going to gather all the details around network interfaces, configuration, connectivity, the disks that are in the host, all of the details around the host, which you can potentially then use for validation before going to the next step, which we're about to show. So you can see once it's been through the inspecting phase, it then becomes available. And at this point, the bare metal host can be consumed for cluster creation. And so for some reason, one of the hosts takes slightly longer in this demo, but I'll just wait for that one to catch up. So we can see now we've got three hosts which are in the available state. In this case, we've actually got two Dell machines, so they're connected via IDRAC Virtual Media, and then we've got one which was, I think, a Supermicro connected via Redfish Virtual Media. And so the next step is we're actually going to provision a cluster. We've got three available hosts. They're ready for consumption to provision a downstream cluster. So we're going to go and create the CAPI resources that I was just describing. We'll give a quick overview of what those resources look like, and then we'll show the cluster provisioning flow going from end to end. Okay, so this is the cluster resource that I was talking about a moment ago. Ultimately, this gives you the top-level description of things like networking for the whole cluster. And then also, there's the control plane endpoint here. This is the endpoint we'll use for the load balancer. So you can connect to the three hosts with a single endpoint. And then you can see down here, there's some additional configuration related to the control plane and its networking. And here is the user data. As I mentioned, this is very flexible and pluggable. You get the bootstrap data from the CAPI bootstrap provider, but you can actually provide any kind of additional user data for the first boot tool. In this case, SLE Micro 5.5 works with a tool called Ignition. So this might look a bit unfamiliar if you're more used to Cloud in it, but it works the same way. You provide some data which describes the first boot configuration. In this case, we're basically injecting some MetalLB configuration via some files. In the future, I think it would be nice to have this abstracted behind the control plane provider in Arcade 2, but as of this point, it is inline additional configuration. So this is going to install the MetalLB Helm chart. It's going to apply some additional configuration that basically brings up that load balancer as part of the downstream cluster. So you can see here, there's a couple of additional configuration resources related to MetalLB. We're describing an IP pool and an L2 advertisement, which is part of the API for MetalLB itself. Okay, so you can see here, these are the actual endpoints we're going to interact with on the deployed cluster, and this again is going to be configured so we can access via the load balancer. We're going to deploy RK2 version 1.28.3, so you can see this is a slightly old demo because that's not the latest version, but that is going to be the baseline we install, and then in a moment I'll show you how you can do an in-place rolling upgrade without any additional hardware. So we're going to deploy using SLE Micro 5.5, as I mentioned, and again, this image could be customized. You could use the Edge Image Builder tool I mentioned earlier on to apply additional customizations depending on your environment, such as additional packages or additional configuration changes that you don't want to handle via first boot configuration. So very simple, we've applied the manifest. This could also equally be applied via a GitOps workflow. And then it's created those resources that we talked about, cluster, control plane, and machine resources. And this is going to result in the cluster being deployed. So this is a bootstrapping process where we've edited a little bit in the interest of making this not too long in terms of the demo flow. But you can see here that we're deploying initially one bootstrap host as part of the 3-node cluster, and then it scales up until you have 3 cluster hosts, and we'll then have a fully deployed and bootstrapped RK2 environment. So you can see the first host has now been provisioned, and that has been consumed by one of the machines, which is part of the cluster definition we were just looking at. So now this is going to scale up, and we're going to see the other 2 hosts become available. So this is now going to start provisioning. So yeah, you can see it's now scaling up to 2 machines, and then it will then, as a final step, scale up to consume the 3rd host, and we'll then have a full highly available cluster. And we'll prove that it's highly available by killing one of the nodes and checking that everything is still working fine. Okay, so now we're just waiting for the 3rd one to provision. Okay, so now you can see it scaling up to 3 replicas, and at that point, once this final provisioning phase is completed, then we will have a full cluster ready for the next step. I'll skip forwards a little bit just so we have time for questions at the end. So this is the 3rd host, it's now provisioning, and this is all orchestrated via the RK2 control plane provider, basically. And so in the CAPI model, the control plane provider is responsible for the management of the control plane hosts, and that's what's happened in this case. It's taken the necessary steps to scale up until you have a 3-node cluster, which is required based on the replicas in the initial manifest. So there we go. This is now up and running. Okay, so we can see now, skipping forward slightly, the 3 machines are now up and ready. The cluster is running. You can see there the timestamp. I mean, that's highly dependent on the environment, how fast the connection is to download images, and what the power on self-test time of the hardware is like. But the entire process end-to-end in this environment took 42 minutes. So I don't know, there's probably scope for optimization in terms of wall time there, but it gives you a feeling that, you know, from 0 to having a fully functioning cluster can definitely be achieved within, you know, a relatively short time, despite it being on bare metal, which obviously is much slower to provision than most VM environments. So we can see now we've achieved our goal. We've deployed a 3-node compact cluster using SLE Micro 5.5 and RK2 128.3. It's up and running, and we can see in the left-hand pane at the top that the 3 nodes are ready. So what we're going to do now is we're going to kill off one of the RK2 server processes, and this is simulating a node failure. So, you know, one of the hosts has failed or has lost power or has some other kind of an issue, and this is simulating you know, that event. So we're going to kill off the RK2 server process on one of these nodes, and then we will see that the node actually goes into not ready state, and that proves that the API connection to the downstream cluster is still working, because we're actually accessing, to read the list of nodes, we're accessing the downstream cluster. And so you can see now one of these is not ready. It's in a degraded state, but the cluster's still up and running, other than the fact that one of the nodes is down. We'll then restart the server, and then we'll see it all come back up, and then that's effectively a simulation of a node outage. All right, so we can see now that's now recovered. We restarted the RK2 server, the node's ready again, and everything was still working fine. So that's proven the high availability side of things, not that exhaustively, but it gives you an idea that, you know, the demo is working as expected. The next step is we're going to do a rolling upgrade. So this is obviously quite a common requirement operationally. The way it works in Cluster API today is it basically does a rolling node replacement. There are 2 ways you can approach this. It can either consume an additional host from your environment and scale up and scale down, or in this case, we're going to configure it to do a rolling upgrade in place, which is what that max surge parameter means. Basically, we're not going to consume any additional hosts. We're just going to do a rolling in-place replacement. So similar to the previous example, you'll end up in a 2-node degraded state for the duration of the node replacement. So we're going to go through, change the Kubernetes version from 128.3 to 129. which isn't actually supported in the Edge solution, by the way, at this point, but it's for the purposes of the demo, that was the version we chose. And we're going to see this go through and do the rolling reprovisioning of the host. I mean, there's pros and cons to the reprovisioning aspect. One of the nice things about this is every time you do an upgrade, you eliminate any possibility of config drift, and you're making sure that out-of-band modifications to the hosts are really not possible. But obviously that requires an operational kind of shift to make sure that all of your configuration is managed via the GitOps workflow and not via manual configuration changes. As I mentioned, upstream in the cluster API community, there is some work looking at in-band updates as an alternative, and providing other options, but for this demo we're showing the replacement strategy. So you can see here we're going through replacing the nodes one by one. We can see one of them has been reprovisioned, and you can see by the version at the bottom it now says 129.0. It's going to go through and replace the other two hosts. So you can see now one of them is about to be reprovisioned again. There we go. It's reprovision. We've now got two 129.0 downstream cluster hosts. And then we'll then do the final node, and then we'll be able to prove via the Kube API that everything's fully upgraded and it's running the new version. All right, so now we're just going to check the actual version via the Kube API to confirm that that's all as we would expect. So there we can see we've got the three nodes we had before, the version has been updated, and that was a fully orchestrated rolling in place upgrade handled via cluster API. All right, so that's the end of the presentation. We've got some time for questions. If you want to find more information about what I was describing today, I know it's quite a lot of information to absorb in a short session, but there were several other excellent talks this week. One of them is actually happening now, and then the other ones have already happened, but you will be able to catch up on the recordings when they're published. You can have a look at the SUSE ATIP session, the 1222, is describing a more advanced use case than this one, but using the same tools and techniques. So that would be for deploying telco workloads with heavy customizations at the OS layer for latency sensitive environments. And then if you're interested in the image building part of the process, then there was also a talk on that where you can deep dive into more details. If you want to have a look online, there's a few links there as well. The upstream cluster API docs are actually really good if you're interested in understanding how that all hangs together. There's also some nice docs in the MetalCube community. And from a product point of view, we've got some nice docs on the SUSE.com documentation site that you can dig into. So any questions as a result of all of that? All good? Well, thank you very much for your attention. Hope you had a great week.